So, let us continue with the earlier class where we have done the theories of the sensitivity analysis, that is for changes in different parameters. What are the ranges for which the optimum solution and the feasibility will remain unchanged. Also, if I add one variable, what happens, or if I add one constraint, what happens. So, let us take one example in the quickly, let me look after. Already I have discussed this problem. So, this is your problem, maximize this subject to this. This we have told maximize z equals this one subject to this, and I have to, we have given the 5 different questions over here. Let us take the questions one after another. The first one, if you see, the first one is find the optimal product of the mix, optimal product mix and the corresponding profit of the company. Or in other sense, if I have to say, I will tell that you just find out the solution of the simplex problem whatever we have given. So, your simplex problem was this, we have 2 less than equals constant. So, whenever I try to write it in the standard form, I have to add 2 slack variables over here x 4 and x 5. So, your problem is maximize z equals 3 x 1 plus 5 x 2 plus 4 x 3 subject to x 1 plus x 2 plus x 3 plus x 4, this is equals 4. Second one is x 1 plus 4 x 2, x 1 plus 4 x 2 plus 7 x 3 plus x 5, this is equals 9. X i's are greater than equals 0, and in this case, if you see here, it will be 0 into x 4 plus 0 into x 5. So, your original problem is this, which you have converted into standard form, maximize z equals this by introducing this one. So, as usual, initial basic feasible solution will be x 1 equals 4, x 5 equals 9. So, that your basis will be in basis you will have 2 variables x 4 and x 5. So, once I am writing these 2 variables x 4 and x 5, say this will be your a 4 and a 5. We will not spend more time on this because we have done all these things earlier. 3, 5, 4 objective coefficients we are writing here. So, a 4, a 5, it will be 0, 0. Your b is 4 and this is 9. So, b is 4 and 9. So, it will become 1, 1, 1, 1 and 0. Second one is 1, 4, 7, 0, 1. So, you calculate zj minus cj, zj minus cj will be minus 3, minus 5, this will be minus 4, this is 0, this is 0. So, most negative is this one, therefore, your entering vector will be x 2. So, we have to calculate the ratio, this is 4 by 1, this is 9 by 4. So, your outgoing vector is x 5. So, your entering vector is x 2, outgoing vector is x 5 and your pivot element is 4. So, I have to make this element as 1 and the other elements as 0. So, in the next table your x 5 will be replaced by x 2. So, let us write down the next table. In the next table your x 4 will remain as it is, you are having now x 2. So, it is a 4 and a 2. Your C B is 3, 5, 4, 0, 0. So, x 4 is 0, x 2 is 5. Your vectors will be, the rows will be after manipulation 7 by 4, 3 by 4, this will be 0, minus 3 by 4, 1, minus 1 by 4, and this will become 1 by 4, 1, 7 by 4, 0, 1 by 4, sorry, the B is 9 by 4. So, 9 by 4 means this will be 1 by 4, this will become 1, this will be 7 by 4 because this has to be 1, x2 was the entering vector, 7 by 4, this will be 0, this is 1 by 4. So, if you calculate Zj minus Cj, that is Cb into B minus Cj, this will be minus 7 by 4, 0, 19 by 4, 0 and 5 by 4. So, again still your Zj minus Cj is less than equals 0. So, entering vector will be x1. Now, calculate the ratio. This will be 7 by 3 and this will be 9. So, outgoing vector will be x4. So, your pivot element is 3 by 4. So, I have to make this element as 1 and this element as 0. So, your x4 will be replaced by x1 here. So, you are coming as x1, x2. Your B values are a1, a2. So, your Cj are 3, 5, 4, 0, 0. This is 3 and 5. So, the rows will be 7 by 3, this will be 5 by 3, 1, 0, minus 1, 4 by 3, minus 1 by 3, and this will be 0, 1, 2, minus 1 by 3, 1 by 3. You should check whether the values are coming correctly or not afterwards. So, now if we calculate Zj minus Cj, Zj minus Cj will be 0, 0, 3, 7 by 3 and 2 by 3. So, Zj minus Cj, if you see, this Zj minus Cj is greater than equals 0. For this case, Zj minus Cj is greater than equals 0 for this, and it is 0 for basic variables, greater than 0 for non-basic variables. So, you are getting the unique optimal solution. X1, X2 is present. So, your optimal solution is X1 equals 7 by 3, X2 equals 5 by 3, X3 is not present, therefore, X3 will be 0 and maximum value of Z star is equals to this into this, that is 3 into 7 by 3 plus 5 into 5 by 3, other term will be 0. So, that value you will get as 46 by 3, and this is nothing but tentatively I can write down 15.33. So, one can say that to obtain the maximum profit of rupees 15.33, the product X has to be produced 7 by 3, a product Y should be produced 5 by 3 units, and no product should be produced for the product Z. So, please note that to obtain the maximum profit 15.33, one has to produce 7.3 unit of product capital X, 5.3 unit of product capital Y, and no unit should be produced for this one. Please keep this one in mind, this particular table, the last table, because in the next 4 problems we will use this thing. Frequently we will use this optimal table. Now, come to the second problem. The second problem is find the range of profit contribution of product X and Z in the objective function such that current optimal product mix remains unchanged. That means, what should be the variations in or what range of profit contributions of X and Z, so that it remains unchanged. For the product X, what happens? Corresponding variable, as you know, it is x1 and the coefficient is c1. So, from optimum simplex table, that is what I was telling, your x1 is present in the basis, right. So, your cost is C1. So, if we decrease C1, what will happen? Current optimal product mix will be affected, and if we increase C1, in that case beyond a limit it will make the product X much profitable and enforces decision makers to produce product X only. So, please note this one, since X is lying in for the product X, corresponding variable is X1 and it is lying in the optimal solution, in the basis it is present. Therefore, if we decrease the value of C1, then the current product mix or the basis will be affected, whereas if we increase C1, in that case it will be much profitable and it will enforce to decision maker to produce maybe X only. Thus, what I can say, for increment or decrement of C1, optimal policy will be affected. Optimal policy will be affected. We have to find the lower and upper bound of C1 for which optimal solution will not be affected. So, by these two, what we are showing, that whether I increase or decrease the value of C1, optimal policy will be affected. So, for what range of C1 optimal policy will not be affected, that we will calculate now. Range of delta C1, if you remember, this is from the earlier lecture already we have told, maximum of minus delta j minus zj minus cj by y1j, here it will be, which is greater than 0, less than equals delta C1 less than equals minimum of minus zj minus cj divided by y1j, where y1j will be less than 0. So, what are these values? Maximum of, you are doing it for which one? For product 1. See this table, in this particular table you try to find out maximum of what you will obtain. This will be 0 by what, where it is most positive. Most positive is coming here. Your zj minus cj for the variable it is 0 and here it is 1, or the positive value here it is coming as 1. So, therefore, zj minus cj, and for this case y1j has to be, I will take only that I for which y1j is greater than 0. So, therefore, maximum is 0 divided by 1. So, the value will be maximum of minus there is no need 0 by 1, from where you are getting 0 by 1, from here only you are getting, this is 0 value divided by 1, and there will be another one where the value of yj is positive. For this positive value zj minus cj is 7 by 3 and this yj value is positive greater than 0. So, therefore, the other one will be minus 7 by 3 divided by 4 by 3. This should be less than equals delta C1 less than equals minimum of, here I will take only those yij's ratios where yij is less than 0 in the optimal solution, where yij is less than 0, one is this one, that is zj minus cj by yij. So, this will be minus of 3 divided by minus 1, this is your 3 divided by minus 1, other one it is 0 on this. So, it will be minus of 2/3 by minus 1/3. So, this will be minus 2/3 by minus 1 by 3. So, like this way, these values yij, zj minus cj values I have to prepare. I hope it is clear now that y1j means for the first one you are taking it wherever you are getting the positive values, and for the minimum value y1j value should be less than 0. So, if I calculate this, you will get minus 7 by 4 less than equals delta C1 less than equals 2. So, value of C is this one, value of C for this problem is 3. Therefore, 3 minus 7 by 4 less than equals C plus delta C1 less than equals 3 plus 2, which implies C1 star or new value of C, if it lies in this range, in that case there will be no change in the optimal solution. So, you see the original problem. In the original problem, coefficient of the product X was 3 C1, right. So, 3 was there. Now, if I change this 3 value coefficient from in between 5 by 4 to 5, in that case your optimal solution will remain unchanged. So, here your advantage is, if I have changed C in this range, I do not have to recalculate the problem. Similarly, for the product Z, what happens? For the product Z, if you see, your product Z means which corresponds to the variable x3, and x3 is not present in the basis. Your x3 is not present in this particular basis. So, therefore, the calculation which we did earlier, that will not be applicable for product 3, because here this is not in the basis. Only thing I have to check Zj value, Zj minus Cj, that is Z3 minus C3 value should be changing. So, what I have to calculate for the product Z? For product Z, the variable is x3. So, I have to only check the optimality Z3 minus C3 minus del C3, this should be greater than equals 0, because C3 now has been changed to this one, C3 has been changed to C3 plus del C3. So, this should be greater than equals 0, which implies immediately you can tell that del C3 should be less than equals 3, since Z3 minus C3 is nothing but C3. So, therefore, your C3 less than equals C3 plus del C3. From here I can write down C3 less than equals 4 plus 3 or C3 less than equals 7. So, your original value of the coefficient for x3 was 4. What is our conclusion now? Till the value unit price for the product Z, which is C3, if it up to 7, if we change it to up to 7, there will be no change in the optimal solution. So, please note this one, that there will be no change in the optimal solution. Now, come to the third one. The third one is, what shall be the new optimal product mix when profit unit per product Z is rupees 13 instead of 4. That is, earlier for per unit cost for product Z was 4. Now, if it increases to 13, what happens? Now, if you see, I am coming to this, if you see, whenever your C3 is changing from 4 to 13, so obviously your Z3 minus C3 will also change. What is your Z3 minus C3? Z3 minus C3 is nothing but CBY3 minus C3, and CBY3 is 3 5. This I can obtain from this one, CB and Y3 is minus 1 2 minus 13. If I calculate, this value is this one. Effectively, I am doing from this. Zj minus Cj is nothing but CBB minus Cj. So, Z3 minus C3 is less than 0. So, current optimal solution will not remain optimum. From here it is clear that the current optimum solution with this value we have calculated this 3, 5 and minus 1, 2. So, with this value minus 1, 2 and after that minus new value of Cj, that is 13. So, it is becoming negative, and since it is becoming negative, so current optimum value will not remain optimum in that case. So, the non-basic variable x3 will enter into basis, that is here you are having this one. So, this will be changed to 13. So, from here, from this one itself I will change it to 13 and then we will recalculate the value. So, basically on this we have shown the value is becoming minus 6. So, if I write it quickly, the last solution, your B is x1, x2, a1, a2, 3, 5. This value has been changed to 13 from 4. Please note this one. So, this is 3, 5, this is 7 by 3, 5 by 3, this one is 1, 0, minus 1, 4 by 3, minus 1/3, this will become 0, 1, 2, minus 1/3, 1/3. So, Zj minus Cj values 0, 0, as I have shown it will be minus 6, 7 by 3 and 2 by 3. So, basically in the last optimal solution you are only changing the value of Cj from 4 to 13 and you are finding that Zj minus Cj is this. So, your entering vector will be this one. So, now calculate the ratio, this is negative, we will not calculate, this will be 5 by 6. So, outgoing vector is a2. So, therefore, this is the pivot element. So, now you will have x2 will be replaced by x3. So, x1, x3, a1, a3, 3, 5, 13, 0, 0. So, here it will come 3 and 13. So, again I am writing this, I have to make 1, this as 0. So, this will be 19 by 6, 1 half, 0, 7 by 6 and minus 1 by 6. This will be 5 by 6, 0, half, 1 minus 1 by 6 and 1 by 6. If you calculate Zj minus Cj, you will find that 0, 3, 0, 8 by 6 and 10 by 6. So, therefore, your Zj minus Cj is greater than equals 0 for all j. Therefore, new optimal solution is x1 star. Now, x3 is out, x1 star is 19 by 6, x2 star is not present in the basis. So, it is 0 and x3 star is 5 by 6 and j star if you calculate 20.33. So, obviously, whenever you have changed the unit price for product Z, that is corresponding to the variable x3 to 13 from 4, we are finding optimal solution changes totally and the profit also has been increased in this case. So, this is the third one. Now, let us see the fourth one. Fourth one, discuss the effect of changes in the availability of resources from 4.9 to 9.4. That is your original problem. If you see, it was 4.9. This I replace by 9.4. Then what will be the change in the this thing? So, for optimality, what happens? Your YB is 7 by 3, 5 by 3. This is again from the last original optimal solution. This is 7 by 3 and 5 by 3. What is your B inverse? B inverse means whatever is not there in the basis, that is x4 and x5. So, B inverse is nothing but we are writing y4 and y5 and y4 is 4 by 3 minus 1/3 and minus 1/3 1/3. So, you are getting from here. So, if I replace 4 9 by 9 4, I am replacing 4 9 by 9 4. So, in that case your x1 x2 is equals to B inverse into B. So, your B inverse is this one 4 by 3 minus 1/3 minus 1/3 1/3 and your 9 4. So, it will become 32 by 3 and minus 5 by 3. That means, your solution is x1 equals 32 by 3 and x2 equals minus 5 by 3. So, x2 is minus 5 by 3. Since your x2 is less than 0, therefore, the original solution whatever you have obtained, that it will be remain unchanged, that will change. Your optimal solution, feasible solution will become infeasible now. So, to remove feasibility, what I have to do? I have to find out the maximum of minus of Zj minus Cj by y2j minus of y2j, where y2j is less than 0. This will be equals to, from the original table, this one minus 7 by 3 and 1 by 3. From here you can obtain it. So, from this table you can obtain the value of Zj minus Cj is this and y is minus 1 by 3. So, these two values if you take, in that case this you take 7 by 3, which is this one, and y2j is less than 0. So, this will be minus 7 by 3 by minus 1 by 3. So, that you are obtaining 1. So, x2 becomes non-basic and x4 becomes basically basic variable. So, from the original one whatever was there, using the other way, x4 becomes basic and non-basic variable. So, here I can calculate this thing. You have x1 x2, you have a1 a2, 3 5 4 0 0, 3 and 5 will come over here. These values you will obtain minus 32 by 3 minus 5 by 3 1 0 minus 1 4 by 3 minus 1/3. I have changed this value. Effectively what I have done, I have changed this b value now 32 by 3 into minus 5 by 3 in the original problem. Here it was 7 by 3 5 by 3. This I am changing it to 32 by 3 minus 5 by 3. All other things will remain same. 0 1 2 minus 1/3 1/3. Zj minus Cj value 0 0 0 0 0 3, 7 by 3 and 2 by 3. Here I have to take the this one minus 1/3 and this will be 1/3. So, this is the outgoing vector, therefore, this is your pivot element. So, in the next one your x1 will come, x4 will come, a1 a4 will come. So, it is 3 5 4 0 0, this is 3 and 0. So, this becomes 4 1 4, 7 0 1 and 5 0 minus 3 minus 6 1 minus 1. Zj minus Cj you will get 0 7 17 0 3. So, all Zj minus Cj is greater than equals 0 for all j. So, you obtain the optimal solution as x1 star equals 4 and x2 and x3 are not present here. So, x2 and x3 star equals this, and z star if you calculate it is 12. So, again for this particular case also what we are finding is that the optimal solution has been changed. So, in the next class we will see the last problem, that is this one we will discuss, which resource we should use, which resources should be increased or decreased to get best marginal increase of the objective function. In the next lecture we will just do this, and after that we will go to the dual simplex procedure.